Okay, good afternoon, everyone. I am sorry for sending the link late. I totally forgot about that. I mean, I was prepared, and then when I wanted to start, I said, oh, there's no link. So I had to quickly send it. So I'm really sorry. And let's begin our lecture for today. Let me share my screen. Okay, guys. Today we will be beginning with lecture 2, which is unconstrained optimization. So basically, what we have seen so far is how to the approach to find a local minimum or a local maximum, or I would call it an optimal point. Okay. Can everyone hear me?
Yes.
Okay.
Yes.
Okay.
Yes,
Good.
yes.
Okay, so what you do is one way to find an optimal point is if you're given some function, you have to check for all possible points on the line on the function and see whether it's a local maxima or local minima by using the derivative test. Okay, so we had the first derivative and second derivative. We'll be talking about it in more details today to generalize that concept. Okay. Another more efficient way to do that is, of course, using the Taylor series. So I believe you all know what the Taylor series is. It's finding the functional point. I'm sorry, finding the functional value in the neighborhood of some, where is my pen? In the neighborhood of some given point x, such that we have the functional value of x, we have the derivative of the functional value at that point, and so forth. So if you have a function which is whose first derivative is continuous and does exist, you can use Taylor series to actually check whether this function, that means for the point x to be, for example, a local minima, every point, the function value of every x plus epsilon value, okay, should be greater than the value of f of x. Okay, so this side should be greater than that. So using the Taylor series, we can prove that. I will actually send you the proof of this once I scan it. Okay, I have written it. I'll scan it and send it to you because typing it is really very difficult in PowerPoint. So I will scan it and I'll send it to you so you guys can see how to prove it, and then that's it. So you can use, if there are two, if it is twice differentiable, then you can actually use the second order term as well in the Taylor expansion. Okay. So now we go back to the optimal condition. So now I'm trying to actually polish the definitions that we have seen regarding the first derivative and the second derivative, and let's give it some fancy names. Okay, so for those of you who are using the internet or Googling or using other lectures to supplement the scores, you will probably hear about these terminologies. So don't be scared, don't be alarmed. These are just simple terminology. These three. The first one is the first order necessary condition, which we abbreviate as FONC. It says that if I'm giving you, if I'm telling you that x star is a local minimum or minimizer of some function f, which is differentiable, then f prime x, that means the first derivative of that function at that particular point, would be equal to 0. So this is something that we have seen. So if it's a local minimum, then definitely the first derivative would be equal to 0. Okay, so we can prove this using Taylor series, as I told you, and I'll send you the proof later on. Einar, please admit the students in the session. So we go on to the second order network condition, which is known as SONC. And SONC says that, okay, if I tell you that x star is a local minimum, that means this information is given to you, okay, and the function f is twice differentiable, okay, then what I can say is, so this is a necessary condition, keep in mind, okay, that the first derivative at that point, so this is x star, guys, okay, this is not x, this is x star. The first derivative at that point, x star, would be equal to 0, and the second derivative would be greater than or equal to 0. Greater than or equal because it's a local minimum, okay? If it was maximum, it would be less than equal to. Okay, so this is a necessary condition, and we know that necessary and sufficient conditions are required to make sure that a case actually holds. Okay, so now let's look at the sufficient condition, which we abbreviate as SOSC. Sufficient condition is just the opposite. So in the first two conditions, I told you that I'm giving you that X star, or I'm telling you that X star is a local minimum. And then if it's a local minimum, then these conditions would hold. Now over here is the opposite. I'm saying that if the first derivative at some point X star is equal to 0, and the second derivative at that point is greater than 0, then only we can say that X star is a strict local minimizer. Okay, so it's just the other way around. So we have a necessary condition, but to make sure that it is true for some point X star to be a local minimum, we should have the sufficient condition as well. So basically, the sufficient condition is a kind of more stronger condition as compared to the necessary condition. Okay. Now let's look at the definition of convexity. So I briefly explained it, or I briefly introduced it to you in the first lecture, okay, where I said concave up, concave down, which corresponded to the growth or the decrease or increase in the slope of a function. But here, let's make a more formal definition, okay? So basically, in optimization, what you do is normally you're given some function, f of x, which in this case, say, is this line, okay? Or this line, okay? And this is a function. So basically, this function has a curve because we are finding the local. So in order to find the local or global optimal point, there should be a valley like here, or there should be a peak as over here, okay? So, and if there is a valley or a peak, then obviously there will be some point at which the slope would be 0, and that point would be actually a critical point, okay? So we are interested in finding such points in some functions which have a curve, whether a curve down or curve up. So if the curve is down, this is called a convex function. If it is up, it's called a concave function, okay? So this is just basic definition. And if you want to represent it mathematically, what I can say is that if we are given a convex function like this one over here, okay? So all these points, so pay attention. So this is f of x, this curve, and we're given 2 points, say xa and xb, okay? And so this point is f of xb, right? Because it is corresponding to the f value, and this point is f of xa, okay? So how do you define a convex function? A convex function is a function if given any 2 points xa and xb, there exists some theta value, okay? So every point on this curve I'm just drawing, okay, between these 2 points, xa and xb, okay? So the functional value of every point on this red line that I have highlighted, okay, should be less than equal to the sum of the functional values at xa, xb, or any point on this dashed line, okay? So that means the local minimum should, so every point in this curve below the straight line connecting xa and xb should have a functional value less than or equal to xa, xb, okay? So at this point, the functional values would be equal, but for every other point, the functional value on the straight line would be greater than any point on the functional value, or any point on the curved line. Would be less than or would be greater than or equal to the functional value of any point on the curved line. Is it clear?
Yes.
Okay. So if you have any question, please just stop me and ask me right now, okay? The same works for the concave. So if this highlighted curve that I'm doing over here, this basically is this function. So it's saying that the function value of every point on this highlighted curve should be greater than or equal to the functional value of every point on this dashed line, which is connecting xa and xb. So if that's the case, so that means there will be a maximum point here, and there'll be a local minimum point over here. So this is how you define a concave or convex function, okay? So if you have a concave or convex function, definitely there will be some optimal point in it. Now let's pay attention to convex function. The reason is why not? The reason is because as I told you, every concave function can be converted into a convex function by just flipping the sign, right? So if you change the sign, it would just be the same of this. So it would. So there's no point in. So if we all we need to do is just focus on one type, and we can easily change it to find the optimal point in the other function. So let's say we're looking at a convex function, which is a value function as shown over here. So we know that as the value of x increases, as we move along the x-axis, okay, the slope of the curve, the slope of the curve increases. That means there's a negative over here, then it becomes 0, then it starts increasing, right? So at the point, so that means we are going from negative to 0, and then we are going to positive. So that means at some point it will become 0. And at that point, which is 0, it is actually that is the local minimum of that convex function, okay? Similarly, you can have a same argument for the concave function. So if it's the opposite way, so that means the curve is not the slope is not decreasing but increasing, then becomes 0 and then starts decreasing. So if you have a function like this, then the slope would be increasing. At some point, the slope would be 0, and then the slope would be decreasing. Okay, so it has the same argument. In that case, we would find the local maximum. Now let's look at an example. Now this is something I want you to, Ainur, are you there?
Yes, Professor, hello.
How are you? Please admit the students because it's every time it's coming in front of my screen, I get distracted. I think
yes.
there's some. Are you?
Yeah.
Okay, thank
Don't worry.
So there are 2 students waiting now. Let's look at this example. So we have f of x is equal to x to the power 4. Okay. And so what we want to do is we want to study the point or study the behavior of the function at the point x is equal to 0. Okay. So if I plot this function, this would look like this over here. So this is x to the power 4. So let's see. Now, I have told you about the derivative test and second derivative test, right? So what we saw so far is that if you take the first derivative, it's equal to 0. Take the second derivative, it tells you about the curvature. If the second derivative is positive, then it is a local minimum. If it is negative, then it's a local maximum, right? And if it is equal to 0, then I told you at that point, it is an inflection point. Okay, so now I'm going to kind of extend what I just said, and I'm going to extend what I just said, and we'll see how it works. So first we take the first derivative. So we want to study the function at the point x is equal to 0. I'm given a point. So we take the first derivative and plug in x is equal to 0 in that. So the first derivative of x4 would be 4x cubed, and this would give us 0. Okay. So this is the first derivative test. Now we go to the second derivative test, and it tells me that, okay, I take the second derivative of this, which would, the second derivative of this, which would be 12x squared, and I put x in it, it would give me 0. Now, if we had to base this argument upon, if we had to see what I told you earlier, that means if this is also equal to 0, it means this should be an inflection point. Am I right? That's what I told you earlier. But what we do is, no, we do not stop here because this function is continuous, right? So we keep derivating it again. So we take the next derivative, that means the third derivative, which would be 24x, and plug in x. It's again equal to 0. Is this further derivable? Yes, because this is continuous. So we take the fourth derivative, it will give me a constant value, which is positive. So at here, we know we stop, okay, because this is not equal to 0. Now, so what I'm doing is I'm adding something to the optimality test that I told you earlier, okay? So I told you earlier, we only stopped at the second derivative, and we said, okay, based on that, everything is okay, and we do not have to check further. But that's not correct. What we have to do is we have to keep doing it until we reach some point that when we take the derivative, it's either negative or positive, okay? So at this point, we see that it is positive when we take the fourth derivative of this function. Now, this is very important, so keep this in mind. So as I said that if the second derivative is 0, we must check the higher order derivatives. That's what we did. So the second derivative was equal to 0, and then we check the third and fourth derivative. Now, this is what you have to keep in mind. So you keep doing this until the first non-zero derivative is determined. So if the order of the derivative is odd, then what would happen is that point x, that means x is equal to 0, would be an inflection point. Over here, x is our derivative order is 4, which is not odd, it's even. Okay, and we know that it has given us a positive value, 24. So that means we would go for this case. So the first non-zero derivative for which the value is not equal to 0, okay? And that means if it's positive, that means in this case, it would be a local minimum. If it is negative, it would be a local maximum. So you have to pay attention to the order of the derivative. Okay, so if, for example, taking the third derivative would give me a non-zero value, then I would say that this is an inflection point. I mean, without doubt. But if it is even, then you have to check. If it's positive, then it is local minimum. If it's negative, it's local maximum. Okay, is it clear? Okay, so now you may ask me, okay, then what about the question that we had earlier? In the first slide, we had f of x is equal to, this was the case, x5 to the power 5. I'm just repeating it over here, x4 minus 2x cube. Okay, now I want you to check this at the point x0 is equal to 0. Okay, so what you do is take the first derivative. The first derivative and plug in x naught, it would give you 0. You take the second derivative because it's still further differentiable. You put x naught in it, it will give you 0. You take the third derivative, you put x naught, it will give you minus 12. You can work it out and you will see. So minus 12 is less than 0, and this is for the, excuse me, third derivative, dash, dash, dash. Okay, so we see the order is 3, and we said that if it is odd, then this point would be an inflection point. And if you go back to the example in the lecture 1, you would see exactly, I also told you that that is a point of inflection. I didn't tell you that's the point of inflection because the second derivative was equal to 0. I told you because I knew that in future, in the next slide, I would be explaining this to you, and it would definitely be a point of inflection. Okay, is it clear? Okay, now I want you to tell me what would be, I've told you everything over here. So now I'll give you an example, and I want you to tell me whether that point is x cube. Sorry, this is Control C. This doesn't work. Control C doesn't work. Raise. Okay, so I want you to, this is 3. I want you to find me the, find me the roots of this function and tell me whether it is a local minimum or local maximum. F of x is equal to x cubed. I want you to do it right now, and I'll ask you in 2 minutes.
It's an inflection point.
Tell me what it is. I've given you a function, check it, just as we have done over here. So what you have to do is first you have to find the points at which it is equal to this function touches the x-axis, the roots of the function.
0.
Okay, so now tell me at the point x naught is equal to 0, whether this function, or what's the behavior of this function? It is a local minimum, maximum, or stationary point?
It's a stationary point.
Why is it a stationary point?
Local minimum.
One by one, the gentleman who's saying it's a stationary point. Why is it a stationary point?
Because the second derivative is also equal to 0.
Okay, so the first derivative of this guy would be x, 3x squared, okay, and you plug in x is equal to 0. This would be equal to 0, right?
Yes.
This is the first derivative, f prime. The second derivative would be 6x, right?
Yes.
And 6x is also equal to 0 if I plug in 0. But should we stop over here?
No.
No.
Why not?
So we go to the third derivative.
Because 6x is still differentiable, right?
Yes.
So we go to the third guy. That means I'm writing it over here. F third derivative of this guy, which would be equal to 6. 6 is positive, right? So if the order of the derivative, so it's positive, we know. So we stop over here. Now we look at how many times we have taken the derivative of the function. We have taken it 3 times. So n is equal to 3, which is odd. And since it is odd, it would be a point of inflection. Okay, so you have to explain it like this in your exam. Just don't tell me it's a point of inflection. I know it's a point of inflection, but I need to make sure that you understood why it's a point of inflection. You just randomly gave me an answer. Okay, so this is how you would write it in your exam. Is it clear?
Yes.
Okay, no questions? Could we move on?
I have a question.
Yes, sir.
Can we explain it in terms of concavities? Or we can just take a second derivative of a function, and if the concavity changes from concave up to concave down, or vice versa, we know that this is the point of inflection. Can we do that? Instead of taking, instead of this approach, can we take that kind of approach?
Can we take, so you're saying that taking the second derivative, and if the second derivative is 0 and you draw the function, that's what you're saying? You draw the function of the second derivative, and based on that, you tell me the answer?
Well, not necessarily to draw. I was thinking that if the second derivative is positive, it means concave up. If negative, concave down. And I thought maybe if concavity changes, in that case, we can say it is point of inflection. But now
What if the
I'm
second
thinking that-
derivative is 0?
Yes, that's what I'm thinking now.
Yeah, so if
Yes,
it's 0,
you're
you
right,
cannot
you're
say
right.
anything, right?
Right.
So these
yes.
examples that I've given you, you see the second derivative is 0. If you can stop it, because if it's convex or concave, definitely your second derivative would not be 0. But if it's 0, you have to keep doing that. Okay,
Yes.
good.
Actually,
I'm
Sorry?
sorry?
did you hear me?
Yes, please speak out loudly. You have a question?
Yeah, I want to comment on the question.
Yes, please.
So you can just find the first derivative and you equate it to 0. And then you find the roots. And then after that, you plot it on the X line and then find the signs of the derivative function on the intervals. If the sign do not change, it's an inflection point. If sign changes from plus to minus, it's a maximum point.
So how do you define the interval?
Intervals are likely between the roots of the first derivative. For example, in this example, the first derivative is 3x squared, right?
Yes.
So we plot it at the x-axis, and we check the sign before 0 and after the 0. On both sides, it's plus. It means sign doesn't change, and it means it's an inflection point.
At both sides, it's plus. Yes, we can do that. Yes, you're right. But keep in mind that these examples that I'm giving you are very simple examples, right? I mean, these are some examples with just one function, one variable, and you're just plotting it. So if I give you something, for example, I give you a function that finding the derivative is very challenging, or finding the second derivative is also very challenging. That means it's not that easy. And it would not be a good idea to use this approach. And that's what I'll be talking about today, okay? So if the functions are as simple as this, yes, you can do that. You can take the second derivative, the first derivative, find the roots, and then between the intervals, you check the sign, the continuity of the sign. And based on that, you can decide if it is true or false, okay? But I'll be talking about this in details today, and to justify why this approach is good, but not always the best approach, is because the functions given over here are simple. If the functions would be a bit more complicated, probably even plotting them, as you mentioned, would not be that easy. So we have to come up with different approaches, all right?
Yeah, I agree. I'm just...
Yes, I agree with you. I understood what you're saying. That's true, yes. Okay, but the main objective of this slide was to try to generalize what I told you earlier, that because earlier I only stopped at the second derivative and I told you that you can make a decision at this point. But this is not true. Okay, if the function is continuously differentiable, at some point this would definitely give you a positive or negative value, right? And that's when you make a decision. Okay, so for example, if I had to stop over here, okay, that means I would say, okay, I did the first derivative test, the second derivative test is equal to 0, so this guy would be a point of inflection. Finished. Ta-da. Okay, but that's what I told you earlier, but that's not true. You have to take the third derivative, fourth derivative until it is non-zero, and then you check the order of the derivative. It is odd, then it is an inflection point. Whether this is less than 0 or greater than 0, it doesn't matter. But if it is even, then the sign of the value that you get matters. Okay, and that's when you can make a decision. So basically, if I had given you this example in lecture 1 and asked you to find, you all would have said that, okay, this is a point of inflection at x is equal to 0, which is not true, right? Okay,
Yes, yes.
any questions? Okay, this is a quick example. I want you guys, well, I've written the solution also over here, so just quickly go through it. So I've given you a function a, b, and c. These are some constants, coefficients, and what we do is you take solve it for f prime x is equal to 0, find the values of x. So the root would be minus b divided by 2a, and then we take the second derivative of this guy, okay? Because why do we take the second derivative? Because the first derivative is still continuous. When you take the second derivative at this point, we found this point, okay? We would get 2a. Now, depending on the value of a, whether it's positive or negative, the x prime would be either a minimum or a maximum point, okay? So go through this example, very simple, okay? So we found the root over here, plugged it into x second derivative, we found 2a, and then based on the sign of a, we decide on whether x star is minimum or maximum point. Okay, so this is some, let's quickly let's quickly revise or try to refresh our memory on some basic operations, okay, in calculus that you must have studied so far. Up to now, we have seen functions that have only one variable, some scalar variable x. Okay, so basically, it takes some unknown variable x, and it's a function of f of x. So this is what we call a univariate case. Okay, that means only one variable case. But what if you have more than one variables? Okay, so that means your independent variables are more than one. So let's say we have such a case where we have two variables. So it's a function mapping from R from the domain of R squared to R. That means we have two variables, which gives us one scalar value as the return value, which is z. Okay. So in this case, what we do is we deal with partial differentiation because we have two dependent variables and we partially differentiate the function with respect to each of these variables. So we all know what partial differentiation is. That means you have a function. If you partially differentiate with respect to x, y is some fixed value. You do not care about it and you only differentiate the x variable. And partial differentiation with respect to y is just the opposite. So it's basically, if you want to define it in terms of limit, this is what it means. Not important. So just know what partial differentiation is. Now, what happens if the function is, over here, what we had is a real valued function, okay? So a function where the values or the variables are real variables, okay? Now, what happens if we have a function where x and y, okay, are where the arguments of the function are itself functions of x and y. So I denote this by some function of x and y where they are vector valued functions. That means we are going from one function to another function, okay? So what we do over here, again, we define the partial differentiation, but the notation is different. So the partial differentiation of this function, big f x y, would be the partial differentiation of the first function inside with respect to x and the second function with respect to x, okay? Because we are differentiating it with respect to x. So dy f x y would be same thing with respect to, only instead of x, it would be y. Is that clear? And then if you want to derive the Jacobian matrix, so if you take the derivation of the Jacobian matrix with respect to all x and y's, this would be how it looks. So you take the first function with respect to x, first function with respect to y. That would be your first row. Second row would be with respect to the second variable y. I'm sorry, with respect to the second function. So in the first row, you have function 1 with respect to the variables. In the second row, you have function 2 differentiated with respect to the variable. So this is known as the Jacobian matrix, okay? So basically what you're doing is you are taking the transpose of this. So this basically is this, and this basically is d of y, of f of x, okay? So this is dx. That's what you do. If you put it in the matrix form, this is called the Jacobian. So these are things you probably should have learned. So we know what a gradient is. So if you have a scalar valued function for any, so up till now we saw x and y. So r was to the power 2. That means we had 2 variables. Now what if you generalize it to any number of variables, r to the power n, and we want a scalar valued function f that takes us, that maps from the domain Rn to r. Then we define what is known as a gradient. We denote it as such. So the gradient of the function of some vector x would be equal to the partial derivative of that function with respect to each of those variables. Okay, so this would be the gradient, and if we have the vector valued function, that means we have a function to a function, then it's known as divergence. Okay, so it's the same thing, and it is defined as this. Okay, so the second derivative. So if you have a multivariate function and you have a second, you want to find the second derivative, it would be as such. So we call this as the Hessian, okay? So the first derivative is known as the Jacobian, the second derivative is known as the Hessian, and this is how you define it. Now, let's look at the multivariate case. So up till now, we know a univariate, we were able to plot it in an XY coordinate system. Now, if you have a multivariate, it would be a 3D, so something like this. So, you know, this looks like a saddle, something that you put on a horse and you ride the horse, right? So basically now over here, if f of x, so over here now x is a vector, okay? Not a scale, not one single variable. It's a multivariate function. F of x is a multivariate function. So let's assume that this function is at least twice differentiable. Okay, that means if you take this, you take the derivative of it twice, it is differentiable. So the necessary condition for some point x not to be the local minima is that the gradient, that means if you map it to the case of the univariate, this would be actually the first derivative and this is second derivative. But if it is a multivariate, we change the name. So we take the gradient of this function should be equal to 0, as we saw earlier, and the Hessian, which would be the second derivative, should be positive semi-definite. Now, do you know what positive semi-definite is, anyone? What does it mean when I say a matrix is positive semi-definite? Anyone? Okay, positive semi-definite. Do you know what an eigenvalue is?
Yes.
Guys, you should be knowing what eigenvalues are. Okay, I believe you guys should study, okay? So what you'll do today is you'll go and study what, if you're given a matrix, how do you find the eigenvalue of a matrix? Okay, you have a characterization equation and based on that, you can find the eigenvalues, okay? So I will not explain that now because this is your homework and you have to know this. So as I told you, the prerequisite for this course is calculus, linear algebra, and that's it, not even probability, okay? So given some matrix M, you should be able to know what are the eigenvalues, okay? So eigenvalues, so if you have n by n matrix, you will be having n eigenvalues, okay? If it's a square matrix. So the eigenvalue of a matrix is said to be positive semi-definite if all, a matrix, in this case a Hessian, is said to be positive semi-definite if all the eigenvalues of that matrix are non-negative. That means they are either equal to 0 or positive. Okay, so that's why it's called semi-definite. So if you map this to the univariate case, this would be saying, this would be equivalent to saying f prime is equal to 0, the first derivative, and the second derivative should be greater than equal to 0. Okay, so if you remember the necessary condition that we talked about today, the necessary condition, this was the necessary, the first case. if it was a univariate. But if it's multivariate, you just do it in terms of vector. So X is a vector over here, okay? So the sufficient condition again is that, again, the same thing. And the second thing is that it should be positive definite. And when I say positive definite means, unlike positive semi-definite, all the eigenvalues should be greater than 0. That means it cannot be 0, okay? So the similar case over there, and so sufficient condition was that the second derivative should be greater than 0 for this point to be a minimum, okay? And if it was maximum, this should be less than. So basically, this is just generalizing it, or generalizing what we have already seen, the necessary and condition, the necessary and sufficient conditions, okay? Now, so if I tell you the first derivative is equal to 0, so at that point, we cannot tell whether X star is, I don't know, a minimum or a maximum. So at that point, we say that it is known as a saddle point, okay? So in previous case, we call it a stationary point. In the vector case, we call it a saddle point. So this X over here, you see, it's a saddle point because over here it's increasing, but over here it's decreasing. So this point is now, so the derivative over here is, the gradient over here is 0, okay? So we have to find the Hessian in order to determine whether this is positive, the Hessian is positive semi-definite or positive definite, okay? So remember, in the case of univariate case, this point was called the point of inflection or stationary point. Clear?
Yes.
Good. Okay, now let's look at some techniques used to solve univariate optimal. We start with the easiest case. So if you have a function in terms of X, where X is only one variable, not a vector. Okay, so let's look at some problems or some techniques that allow us to solve such problems. So given a function f of X, where X is in the domain of R, okay, so this is a scalar variable. Okay, we want to find the optimal minimum solution. So I've given you a function and I ask you to find the optimal minimum of that function. Okay, so you have to find the point at which the function of that point would have the minimum value. Okay, the functional value would be minimum. So if we had to use the optimality conditions that we have seen so far, what we would do is find the first derivative and solve it, right? Is that clear? We would take the first derivative at that point and solve it. So we find all the X stars for the function and you solve it, right?
Yes.
And then we check the second derivative, right? And we see whether it is a sign of the second derivative positive or negative. So this is what we have seen so far. Now we can actually transform this or actually translate this into an optimization problem. So it would be actually, so what we have over here is minimize, find minimum of f of X. So this is the optimization problem, objective function, okay? And here we have X is equal to R. That means it can take any real value. Okay, so this is my objective function. Now what I'm doing, and there are no constraints over here. So this is an unconstrained minimization problem. Okay, so this can be translated into actually a root finding problem. So it means that if I want to solve this, all I have to do is I have to find all the zeros of this. Am I right?
Yes.
So basically, if I solve this, I have solved this. Хорошо?
Хорошо.
Good. So now let's look at some techniques that actually, so the techniques that we'll be looking at today are the graphical techniques, okay? They are called graph approaches, because what we'll be doing is we'll be using the concept of graphs. As I told you, we are looking at a very simple case, so we are able to graph them, plot them. So these techniques are graphical techniques. Some of them require finding the first derivative, some of them do not require. And we're looking at the pros and cons of each of them. Okay, so there are 4 techniques that we have to study. The first is the bisection method, Newton's method, secant method, and then the regular falsy method. Okay, so the bisection method. Let's begin with the easiest graphical approach. Okay, so this is what we call a bracketing method, and I'll tell you why. Because in this method, in the bisection method, we have to have 2 starting points. Okay, and then we so given 2 starting points, let's say A and B, we can start. Okay, we can apply the bisection method. Okay, now what is the bisection method? Before we get into the bracketing method, the bisection method, which I said is a bracketing method because you have 2 points, and so that means we have some function. Okay, so we have 2 points A. I'm sorry, A is here on the x-axis. This is x, and we have another point B. Okay, so we are given 2 points A and B. Okay, and so that we are bracketing the function within this bracket or interval. We want to find the minimum point. Okay, that means the point which will give us the minimum value. Now, before I get into this, I would like to discuss something with you. Okay, so what I want to talk about now is, okay, I have to stop sharing screen and bring this guy and now start sharing screen. Okay, nice. Do you see my screen, guys?
Yes, you see.
Yes.
Okay.
Yes, yes, we can see it.
Okay, so let's look at the graphic. So before we get into the graphical method, I want to clarify something or make sure that everyone understands what I'm going to explain. So say we have such a, let's use different colors. Now, suppose I have such a function. Okay, so this is my function. Okay, and I've given you 2 points. Say 1 point is this guy. Okay, say let's call it A, and another point is this guy. Let's call this point B. Okay, so I'm going to use this bracketing method. Okay, so this bisection method is one of the bracketing methods. So given 2 points, I've given you a bracket or an interval. Okay, and I want to show you the number of ways in which the roots of the function can be present or absent in a given interval. And this interval is determined by A and B. Okay, so over here, so this is one case. Let me draw all the cases and then I can explain. Let's draw another scenario. Straight line. Assume that this is a straight line. And in this scenario, I would have, say, such a function. And I again take A and B to be these points. So A basically is this point. And B basically is this point, okay? Now, let me draw you the next case. Okay, so in this case, let's say we have something like this, such a function, okay? And let's again take A. This point is A and say this point is our B point, okay? We have one more case. And this is my last, sorry. This has to be a straight line. Okay, say this is straight. And this is tricky. Let me. Okay. And in this case, let's say now this point is again A. And say this point is B here. Okay. Is it clear?
Yes.
So there are 4 cases. Now I just want to talk about the ways the roots can occur. So in this very first case, we see that A and, oh, where's my, there's no mouse here. Okay, I forget the mouse. So in the very first case, let's use orange. We see that this is case 1. A and B, the sign of A and B, that means the functional values of A and B are positive, right? So f of A and f of B is positive. So both of them have the same sign. So in this case, we see that there is no root because this function doesn't intercept the x-axis. Am I right?
Yes.
So there is no root here. Okay, no root. OOT. Now let's look at the second case. In this case, we see that the functional value at A and B are of opposite. Okay, so that means f of A is negative and f of A is positive. So if I write f of A times f of B, it would always be negative, right? if I multiply their signs, their values. Okay. Over here, in this case, f of a times f of b would always be positive. FAFB means a functional value at a and b, okay? Would always be positive. Am I right?
Yes.
Yes.
Okay, so in the second case over here, we see that they have opposite sides. So, and when you have opposite sign, that means it tells me that at some point, this line, this blue line, the function is intercepting the x-axis, okay? Now, how many times it intercepts the x-axis also is, it may be more than one time, all right? So just keep that in mind. So now let's look at the third case. In this case, A and B have positive functional values, okay? So their product would be positive, but they intercept the x-axis. So this guy intercepts the x-axis at 1 point. This intercepts the axis at 2 points. Now let's compare case 1 and case 2, okay? So in case 1, we see that if they are positive, their functional values are positive, or this product is positive, there is no root, or this is case 2. Sorry, this is case 2. Or there are 2 roots, okay? Now let's look at case 4. Again, over here, they have negative signs, and it intercepts 1, 2, 3 times. So we compare case 2 and 4, because they are negative signs. So we see that if the signs, functional values at the given endpoints A and B, if their product of the functional values is negative, then the function intercepts the x-axis at odd, or it intercepts the axis odd number of times. It either intercepts 1 time, or 3 times, or 5 times. Am I right? Can I say that?
Yes.
And if the product FAFB is positive, I say that either there exists no root, or there would be even number of roots. So there's no root in case 1, or there are 2 roots in case 3. Is it true?
Yes.
So I can generalize it, right? But is this true for all cases? Is this generalization correct for all cases? Let me give you a case where actually it is not that. It doesn't hold. Let's say we have this. Okay, now let me draw the function for you. And where's the, okay. So let's say we have a function which touches this guy and goes like this. Beautiful, right? So let's say this guy is A. A, okay. A. And let's say this is B. This point is. Now, over here, we see that the signs are opposite. That means A and B have opposite signs. So it should be either case 2 or case 4, right? That means there should be odd number of roots, right? But look over here. How many roots do we have?
2.
Just 2. So this is not always the case, right? Because this is tangential to the x-axis, okay? It doesn't cut it. So for example, one example where this is true would be, say you have a function, f of x. I'm giving you an example. You can plot it and you can check it. So this happens when you have what we call the case of multiple roots. So if you have x minus 2 whole square times x minus 4. If you plot it, this is what you would get. And the other case is, well, this is a case which is obvious, but I'll just mention it for the sake of completeness. What if you have a function that is discontinuous? Like this, and say some function like this. Okay, so this is a function which is discontinuous, and I give you the 2 points. I say, okay, guys, this is A, okay, and say this point is B. So we see that their product, the functional values have negative, but again, this doesn't hold, right? So such cases can be very difficult if you want to use the optimal test. okay, or even actually the bracketing test. Okay, so that's why you should be very careful, and you should not only rely on one test if you're using the bracketing test or the graphical methods. You should try with at least 2 to make sure that it gives you the right answer. Okay, so this is what I wanted to tell you. Is it clear? Any questions?
Clear.
Good. Do you guys see my slides now?
Yeah.
Okay, so now let's move on. Now that I've told you this, I want to explain to you what happened. Bracketing method. So bracketing method is probably the most easiest method. And in this method, what you do is, if I've given you, so the requirements for this method are 2 initial points, A and B. So if I give you 2 points, A and B, and what you have to do is you have to always test this function. This is the sign of, so the sign changing at 2 points, A and B. So you take the functional value at A, functional value of B, take the product. If it is a negative sign, okay, then do something. If it's negative, it means that these 2 points are on the opposite sides. Okay, one is above the x-axis, the other one is below the x-axis. Is it right? That's why their signs are different. So and why is it important? Because it tells me that at some point, okay, because we want to find a minimum point. So we'll be able to find at least one of the minimum points because they are on opposite sides of the minimum point. So if this is the root of the function, so if I take A to be somewhere over here and B to be somewhere over here, definitely I would get this midpoint. But if A and B are here and here, no chance, right? So it's very important to have the proper initial points A and B. Aresha? So step 1 is, okay, given A and B such that A and B have opposite signs, that is, we know that they are opposite signs of the root on extreme sides of the root, you compute the midpoint. Then you take A plus B divided by 2. So you'll get some middle point over here. Okay, so for example, let's see this example over here. Let me erase this so it doesn't disturb you guys. Okay, so this also erase. Now pay attention to this graph over here because it is good. It's a good graph. So let's start with 0 and 1. I've given you a function, which is a red line, and I've given you 2 points, this green dots. This is 0 and 1. And I tell you to apply bisection method to find the root. Okay. So first thing is I have this, their signs are opposite. So I then take the midpoint. So the middle point of this would be half, right? 0 plus 1 divided by 2 is half. So this would be my midpoint. So now at this new point, I check it and I see, so now I have to replace half with, I have to replace 0 or 1 with half. Okay, so one of these 2 points should be updated with this new point. Which one do I choose? I choose that point which has the same sign as this new point. Because if I choose 0 and in place of 0 I put half, it would give me the problem. That means if I take the function, the sign of these 2 new points, then it would be positive, so I cannot run bisection. So I should replace this new point with one of the old points such that the sign of this new point should be equal to the sign of the one of the old points. Okay, so since the functional value at 1 was positive, function value at half is also positive, so I replace 1 with half. So now my interval reduces. You see, from this it becomes half. So every time I'm dividing my interval, search interval into half. Now again, from 0 to half, so they are opposite each other. So I take the midpoint. So 0 and half, the midpoint would be 1/4. Okay. Now I check the functional value at 1/4, which is negative. So then I replace 0 with 1/4 because they have the same sign. And I keep breaking this. So the next search would be this, 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 until we get very close to our point. Okay. So one other thing that you should know about interval bracketing method is that it doesn't give you the exact point. That means you have to run it for very long in order to get very close to that point, the root. Okay, it would give you some value very close to the point, but it's good enough. Okay, so if you want to quickly calculate it, or if I want to give you an assignment, this is one way to do it. Okay, so keep that in mind. So is the bisection method clear?
Clear.
Good. So the plus points about this method is very simple to implement: finding the midpoint, dividing half, finding midpoint, dividing half, and checking only this condition. And it always, so as long as this condition holds, it will always guarantee that it will get you to one of the roots. Okay, there may be more than one root in your function depending on what are the initial a and b points. It depends. It will give you either of the roots. Okay, so if there are, for example, 2 roots and you choose a and b in such a point in such a way that it is closer to the second root, it may only give you second root, not the first one. Okay. So if you want the first one, you have to randomly again choose 2 initial points and run it again. So you do this running multiple times to make sure to find all the points. So if there's just, so if you're assuming that your model, your function is unimodal, that means you're considering an interval in which we know that there is only one local maxima or local minima. This is called unimodal function. Okay. Then no matter which point you choose, as long as they have different signs, you'll always get close to that root. Okay. The negative thing about this thing is it's too slow. I mean, every time it's binary, so it's log n. Okay, so every time it divides into half, so it may take long time. Okay, and it will only work for functions which have sign changing intervals. Okay, so your function should definitely intercept the x-axis. If it doesn't intercept the x-axis, this won't work, right? Because in that case, this condition will not always hold. Okay, clear, guys? Any questions?
No questions.
Good. Now let's look at Newton's method. Okay, let me see if I have missing anything. So basically, let me recap this. So if the function, so when do you stop? You either stop, okay, when f of a times f of b is equal to 0. It tells me that a and b have become so, I mean, say this, for example, let me erase all. So if if a and b become so close to the root, say this is a and b, okay, such that their sign is equal to 0. Okay, that means they are equal to 0. In that case, we can say we stop. Okay, so the question that no one asked me is that, okay, when do we stop this? How long do we keep doing this? So it depends on how precise you want your solution to be. You could have this as your answer, you could have this as your answer, but if you want to keep it, so what you say is that the difference, the functional difference, so the case would be if f of a times f of b is equal to 0, that's when you have found, or you're very close to the root, and that's when you stop your computation. Okay, or another case is when the difference between f of a and f of b, absolute value of the difference between f of a and f of b, is less than some very, very small value. I don't know why it does that. Is less than or equal to some very small value, say epsilon. So let's say epsilon would be 0.001. So as long as this distance, the difference between this is not is greater than 0.001, you keep doing this. Okay, so you can set a termination condition. So these are the 2 termination conditions that come to mind first. Okay, 1, 2. This guy and this guy. Clear?
Professor?
Yes, sir.
Does the bisection method work if we have more than one root?
As long as the function intercepts the x-axis, yes. It depends, as I said, it depends on how you choose your a and b. So for example, let's say we have this function. Okay, we have such a function. All right. Now, if I choose a and b to be here, then obviously it will give me this point, right? Now, if I choose a and a to be here, and instead of here, I say b is over here. Okay, so it will it will converge to either one of these points, as long as a depends on how you choose the initial values. Okay. I could have chosen a to also be over here, so they are different signs, but then it will only converge to this one, so it will not look at these. If you wanted to look at all, or you want to find all possible. So A and B obviously should be a very larger interval, and every time you have to randomly change A and B to give you this point. Because if you have A and B, it will probably find this because it's bisection, divide into half. If A is here, B is here, it will divide into half. So half is here. So this is very close to this point. So it will converge to this point and not this and this. If you want to find this point, you change B to this point. If you want to find this point, well, A and B is a good choice, or you could have taken A to be here or B to be here. It will give you this midpoint. Okay, so finding A and B is the most challenging part. All right.
Gotcha.
Okay, let's quickly do Newton's method as well. So Newton's method is a more faster method compared to bisection. So bisection, every time it divides into half, so its running time is proportional to log n. But this is this is faster. Okay, this is much faster, and the reason why it's faster because it speeds up in the way it doesn't divide into half every step. It actually in the very big initial steps, it reduces the search interval by a size greater than half. Okay, so but the problem with Newton method is you need to be able to find the first derivative of the function. So your function, if it's a simple one, then it's okay. Finding the first derivative probably won't be a problem for any one of us. But if your function is a weird function, finding the first derivative itself could be hard. So if it's hard, then probably Newton's method is not a good approach. Okay, so what does Newton method say? It says and in Newton method, all you need is just one single starting point. Okay, you do not need two. So quickly explaining it over the graph. So we start with some initial point x naught. Okay, and this point, what you do is you take some point x naught. So your curve is basically the red line. The red line is your function. Okay. So you start with some point x naught. So x naught, you find the functional value of that function. That means what would be f of x naught. Okay. Then at that point, you draw the slope or the tangent. Slope or tangent is the same thing. So at that point, you've solved. So what would be the tangent at this point? It would be the derivative, right? You draw the derivative and find the point at which it intercepts the x-axis. Okay. So the point at which it intercepts the x-axis is given by this function. And that is a change in y divided by change in x. So change in y was basically the functional value. So change in y. And change in x is the derivative. That point, that's the slope, right? So we know that this would be the equation of this blue line, right? So then you find this new point x1. Now, then what you do is repeat the same thing. So you check if x1 is the functional value of x1, whether it is 0 or not. If it's not 0, you repeat the same thing. You find the functional value of x0, that means this point, draw the slope at this point, and find the point at which it cuts the x-axis. So it does it at x2. And you keep doing this until, again, either f of the new point xn plus 1 is equal to 0, or the difference between the 2 points, the last 2 updated points, would be less than some epsilon, just as we saw before. Okay, so this way you see that instead of dividing into half every time, okay, first of all, we have only 1 point. And even if you wanted to divide the interval between half, it does it more than half. So you see it's greater than half. So every time it increases, it doesn't consider half reduction, but more than half reduction. So the reduction is actually quadratic. Okay, so this is the good thing. It converges very fast, quicker. So the running time would be much faster than the bisection method. But the problem is, what if f of if the xn that you choose is a stationary point? Okay, so the x of n is a stationary point. And obviously, the other problem is that it requires finding the derivative. So we definitely need the derivative to calculate the new point. But if the function is difficult to differentiate, then probably this would be a challenge. But other than that, what happens if this x of n that you choose is what we call, excuse me, is a stationary point, okay? So what do you mean by stationary point? That means, say that the second derivative at that point is equal to 0. Okay, so if I want to draw this, let's say you have such a I'm sorry. So say you have some function which is gradually going like this. Okay. So if I take this point as x0, you see that drawing the tangent at this point would be some line which would actually diverge from this point. So it's not taking me to this point, take me away from this point. You see? So it diverges from the starting point. And if I take this again, the tangent at this point, say this function is actually going here. So at this point, and again, this would again draw, if I draw the tangent, it would go again far away. So it will never come towards this point, which is the root. So if the x of n, the starting point that you begin is some stationary point, then this will diverge. All right. I will talk about the other condition which Newton method doesn't work in the next class. For now, this is enough. You have any questions, guys?
No.
Good. So please study. Please look at matrices and see how to find the eigenvalue of matrix. Study positive, semi-definite, positive, definite, because that is part of your exam. That is something I assume you should have already known. All right. Study how to find the eigenvalue and what is the difference between you. There are lots of examples on the internet. All you have to do is just Google. All right, guys. So please remind me next time we start from slide number 13. Okay, just to recap. Any questions?
Okay.
Okay, thank you very much. Take care and all the very best. See you next time. Bye-bye.
Goodbye.
Bye-bye.
Thank you,
Thank you.
Professor.
Bye-bye.
Bye. Thank you.